you will see that he's really a technology, you know. Of course.
All right, sounds good. Thanks, Professor Shi, for inviting me for a talk. Hi, everyone. I'm Ankur. I'm an engineering manager at Uber. Today, I'm going to talk a little bit about how we at Uber are driving sustainability forward. Uber, as you know, has a large presence in US and globally as well, both on the ride sharing as well as each side. So I'm going to talk about two systems that we are building at Uber or have built and deployed. One is connected vehicles and other is green vehicle identification. And through these systems, we'll talk a little bit about how they are helping move sustainability forward. Also, I want this session to be interactive, so feel free to interrupt me, ask questions. It's not a one-way conversation, so happy to kind of take questions as we go along.
How about I ask each of you, they're all my PhD students.
Yes.
Each of you need to ask one question during this presentation, okay?
That's a good goal, yeah. Let's do that.
Including myself, okay?
All right, so a little bit about my journey. So started in 2011 when I came to Columbia to pursue my master's in electrical engineering. I was super passionate about telecommunications and learning about that. One of the interesting things that I did during my master's was blending software engineering with networking. So figuring out how do you use algorithms for optimizing telecommunication stacks and whatnot. And from there, I sort of got into in the industry and started doing systems development at Qualcomm. Within that, helped a few different projects. One of the first one was Qualcomm works a lot with AT&T, Verizon, and a lot of these big telcos in US. So how do you use data to figure out whether coverage caps or how transition is happening from 2G to 3G to 4G to 5G? So building and deploying those networks at scale. Similarly, obviously Qualcomm builds a lot of chipsets on smartphones that go into iPhone, Android, and a lot of these smartphones. So what we did there was figure out how energy is being utilized, because battery consumption is a very big aspect of sustainably using the energy on the smartphone. So we actually were able to file a patent on how certain algorithms were not releasing wake lock on the smartphone, leading to a lot of drainage. And one different project around the patent aspect as well. So Qualcomm has a lot of 3G, 4G patents. So how do you use device counterfeiting, which is a big problem? About $45 billion is lost in revenue there. So building a system to figure out where fraud is happening and manufacturers are not putting in IMEIs in phones. So we'll build a system called DERBS that got deployed. Since then, last 5 or 6 years, I've been at Uber, started in 2018 on the infrastructure team. And as you can imagine, Uber is a massive company and spends hundreds of millions of dollars on infrastructure. Uber is using a hybrid strategy where it has its own data centers, but also uses AWS, GCP, and now more recently Oracle Cloud as part of its hybrid stack. So in this hybrid cloud environment, how do you think about resource efficiency? Which is very important, because if you're not using your hardware efficiently, you're wasting it, which has impacts on sustainability, carbon emissions. So deployed a tool within Uber to help understand where inefficiency was happening and try and optimize that. Similarly, again, forecasting was a little bit on the ML side, figuring out how Uber is growing over the next 3 to 5 years so we can plan our data centers better. And with that, we also created a data lake housing millions and billions of metrics to be used for doing these kinds of analyses. Coming on to my more recent work over the last 2 to 3 years has been on sustainability specifically and on the vehicles team. So as part of that, like we built two systems. One is green vehicle identification. As we think about Uber launching Uber Green, Uber Comfort Electric, a lot of these products which are very focused on sustainability, how do you identify which vehicles are green so that those vehicles should be getting dispatched for these trips? Also, like as most of you are aware, like connected vehicles are a very exciting development where now you can have real-time access to the data coming in from these vehicles. And we'll talk a little bit more about this, but how do you like at scale? Uber has over 6 million drivers who operate daily on the platform, and a lot of drivers have more than one vehicle. So you can imagine like millions of vehicles operate on Uber platform, and a lot of these are connected as well. So building a platform at scale to use that information for building a lot of new cool experiences, and we'll talk a little bit more about that. And battery wear matching being one of them. Similarly, like my team and I also work on catalog. So every vehicle that you get into an Uber platform, my team owns and maintains that. So like the nice icon that you see on the image of the vehicle that's picking up, the license plate for it, all that information like is housed in something internally we call as vehicle catalog. So how do you like scale that up as more and more like drivers and vehicles are coming online, and then extending it for more functionality? So that's a little bit more about me, and we're gonna start off by talking about connected vehicles. So what was the motivation that Uber had for building this platform? So these are like kind of two stats. The most striking one is like 95% of cars that are selling now in US are connected, which means that like as this transition happens gradually to EVs, but also newer vehicles, you will see that more and more like connected vehicles are coming on the platform. And this graph kind of like is showing you that by 2030, we expect like more than 3/4 of vehicles on the road will be connected. So the opportunity is massive here on how do you now use this new real-time information to like tap into it. And even today, if we analyze our current like user base, about 35% of vehicles on Uber platform are connected. So there is already like a real opportunity to tap into that. So what are the potential ways where we can like now use access to this information? Location, I think, is like obviously very important for us. We get it from the smartphone, but the location from the vehicle itself can be very accurate. So for example, knowing like, is the rider on the right side of the road or on the left side of the road? Because now you have very precise location, you can like start building some of that newer experiences. Some things that are like not available at all. For example, maintenance, we have no idea what state of the vehicle is in. So for example, if the driver is driving with an check engine light on, or they haven't like refilled the fuel, all of that could be really important information for us to know on the state of the vehicle, and then nudge the driver to make the vehicle more maintainable and get it to a more safer state. Similarly, like we'll talk a little bit about refueling. Refueling is becoming more and more important for EVs. It takes like hours to charge a vehicle, charging networks are sparse. And obviously, like you don't want to get into a car and then have it in the middle of the road. So knowing that real-time information on how much battery is remaining in the vehicle is actually really important for us. The other thing that is quite interesting is understanding driver behavior. So how is the driver interacting with the car? Are they harsh braking? Did they take an illegal left turn? Did the rider actually like put the seatbelt on when they got into the car? Obviously, like we send a push notification, but we have no real-time feedback to know if the rider actually like buckled the car in. So to make trips safer, this is one lever where we know for certain from the vehicle if the seatbelt is on versus not. So you can already see like there's a whole plethora of new use cases that we can unlock as we go into building like connected vehicles platform.
Gotcha.
Yes.
So as you mentioned, I have two questions. One is, do you have an idea like for a particular vehicle, those are the parameters you are collecting? So how big is the data set?
So we are right now only collecting battery data, so it's only a very small subset. Only battery. But we want to like start collecting more and more of these. So the platform we built is to have petabytes of data that can be stored for all these use cases. Yeah.
Okay.
So we'll go a little bit into design and architecture. So through this, you can see the data set is quite huge. And this can be sub-second data that is coming from millions of vehicles. So you can have like terabytes of data being collected every day. So how do you design a system to support that? So we'll kind of touch a little bit into how we thought about designing the data model. when you think about the data model, there are three basic aspects of how data is structured. The first aspect is metrics, which is the stream of information changing over a period of time on what is the current state of the vehicle, which is like how much battery is remaining, what is the location of the car, how much distance has it traveled, what is the current window state, is it like up or down? So these are like point in time information on the state of the vehicle. Events are similar, but they like talk about change in a state. So for example, like there was a harsh brake in the car, like the passenger put the seatbelt on, or like the driver is like not focusing on the road because now you have like all these sensors in the car telling you that. So those are kind of like change in state events, letting you know about something like asynchronously changed on the car. The third aspect is like actions on how do you like now state change within the vehicle, which is unlocking a door, changing the temperature within the car, or telling it to like go to a certain like latitude, longitude, which is like navigation simplistically. So to support this data model, this is kind of like the architecture that is behind this system. There are kind of two major components here. One is connected vehicles service, and the other one is the gateway service. So the way that to think about this is Uber has basically, you can imagine almost every single OEM out there, and someone is using and bringing that vehicle onto Uber platform. So you can have like multiple different streams of information that you will need to tap into. You need to talk to Toyota, Tesla, Hyundai, Kia, GM, and everyone will have their own like kind of cloud infrastructure to provide APIs. So we kind of bundle that and call that as partners, as our data partners that we will tap into to get this connected vehicle data in. So OEMs are like obviously one category, but you can think of like other ones like OBD dongle plugging into the car to tell you about telematics of the car. You have like rental companies that are like now acting as a third-party intermediary where they are collecting some of this data and we can tap into them. So that whole like pool is the outside world which has connected vehicle data, and we need to connect and get into that. And the service that does that is the connected vehicle gateway. I'll talk a little bit about the cadence, which is the workflow component on how data is fetched. But the other aspects is we need to now have some sort of authorization. So we use a service called UPI internally, which is holding the token for every vehicle, saying this is sort of the OAuth token to get the data from that car and managing that life cycle of the token because it can expire and you need to refresh it. The other thing is like, how do you build adapters? Because as I was talking about, we have one external API that will connect to like one specific implementation, and then you need to build and get the data in a standardized way. So the biggest challenge here is that the battery data may be called battery underscore data structure in like a Tesla system, where it may be like battery data without any like kind of special characters in another system. So it can be like quite varied. So how do you like build a system that can now take multiple different namings and conventions and then like standardize it internally? Because for us, like we only care about knowing what the remaining batteries in the car. So things like that is where the adapter functionality comes in, where you can abstract all of that complexity out and have like a unified way. So now we have kind of like taken all this data from external companies through an external API, and then EdgeGate is our edge computing layer to bring that into Uber ecosystem. So now we have like this standardization layer, which is gateway that is now abstracting and cleaning the data and putting it, and then sending it across to the processing layer. The way we do like the separation between gateway and the actual processing services, we use a Kafka queue. So why we don't have a direct connection, why we use a queue is because what can happen is that you may have like seasonalities in data where in the morning, a lot of Uber rides are happening. So you have like a surge of data. You don't want to directly like send that all to processing. You want to smooth that out. So this sort of Kafka queue acts as like a buffer to smooth the traffic out so that the processing layer is not overwhelmed. It can operate a steady state and consume like a fixed number of messages.
So where's Kafka?
It's running within Uber ecosystem. So these are like kind of two separate services, and they're connected by a Kafka queue.
It's not
No, this is all internal Uber ecosystem.
Assume the data already been collected.
Correct. That's all happening here. And then the API is where the data is going in from the car into Uber ecosystem.
Okay.
Yeah.
Is it happening during the vehicle is running or like it's...
Yeah, that's a really good question. Yeah, and that's a really good question. So the way we do that is we use something called as triggers, where every time a driver goes online on the platform, we use a trigger to say, hey, now they've started operating on the platform. And when they do that, then we call the external vehicle API to get the data. So we don't need to 24/7 collect this data. We only need it when the driver is actually driving on the platform. And this is the component called session checker. The session is like the driver is actively driving. And when the session ends, the data collection stops. So we get another event to know like the collection, the driver has stopped driving. Okay, so hopefully like provides a little bit of taste on, we have a gateway system and we have a processing layer. Within processing, like other things you can do is do cleanliness. For example, if you're getting negative values for battery, doesn't make any sense. It's probably garbage data. So like clean some of the data out to have it more usable.
For the battery, you mentioned right now you're collecting battery for all the
EVs.
EVs, right? So is it okay for you to share with us what kind of data you are collecting?
Yeah, so today we are collecting basically two parameters. One is the remaining range on how many miles are remaining, which is what will show on the dashboard of the car.
Oh, okay. So you're very high level. Just
correct. Yeah, it's very high level because that's all we need. And then also how much percentage the car shows is remaining.
Do we need a special device or you can just read the information?
So for like Tesla has an API that you can hook into to know how much is the battery remaining in the car. And yeah.
How about other from like Chevy Bolt?
So we haven't expanded onto that. And we'll talk a little bit more about other OEMs, but the challenge is that for some of the other OEMs, they don't provide this data more real time. It may be like 15 minutes, 30 minutes. So for the use case we have, it's not useful to know like what the battery was 30 minutes ago. It may have changed. Then how do you know it's fresh? So right now, like our integration is live with Tesla because their system is the most advanced that can give us very real-time information.
So for example, one of my students, so he recently is developing mileage, estimation, fuel estimation kind of algorithm. The support, if that one is already running.
Yeah.
Good. Is it possible for somebody to provide that data to you instead of
correct?
Yeah, for Chevy Bolt, anyway, you can't get it. But if you get second kind of this, and then plug into you guys, so you will get this data.
No, that's exactly where we wanna go. Is if we can't get real-time information, can we like estimate it?
Right.
So if we have like two intervals, and obviously we know through other like the smartphone on how much distance it has traveled, right? So even if the vehicle is not refreshing, you get out other sources of information. So that's exactly like one of the future things you want to do is estimation of battery using data points.
People, okay, question over there.
Yes.
When you collect the data for the vehicles through the APS provided by the factory, do you need some permission from the end users?
Yes, I'm going to talk all about that, like how we build that. Yes, we do need a permission from the user. Yes.
Yeah, and so you mentioned right now you're only collecting battery information, but in the previous slide, connected vehicles have the potential to collect a lot of those data.
Yeah.
So once you are collecting all of those data, is there a mechanism that would prevent the vehicle from over flooding your communication panel, or that's something down the road?
Yeah. Excuse me. Yeah, so that's a really good question. So we built like a feature called smart polling that I'm going to talk a little bit about. So we can control that. So we designed two things. We did design the system to handle that scale. And then one of the things that the system has is two components. One is an online database and one is an offline database. So for example, if we know the battery data, like do we need to like really store it in the database for the last 1 year, right? Like we don't really care what the battery level was 1 year ago. So we can manage some of the volume by saying we're only going to store last 7 days of data in our online database, and everything else can go into like a flat file or like a long-term storage, which is cheap and like and things. So there you can run analytics, but for some of the real-time use cases, you can manage and have your database like be more tight.
Okay.
Yeah.
And then, so a follow-up question on that is, let's say in a certain area you have a lot of Uber cars. So, for example, in a district in Los Angeles, will that have an impact on the other users within that area who are assuming you're transmitting your information via let's say Verizon's 5G network? Will that impact Verizon's other customers because you're consuming a lot of their bandwidth?
That's a good question. I don't think so, because the way it also depends on how the OEM has designed their system. So for example, the way Tesla works is whenever you make a call to get the data from the vehicle, like it's directly going to the vehicle. Whereas in other cases, like the OEM is automatically periodically getting the data and storing in the cloud. So when a third party is making a call to it, instead of going to the vehicle, it's just going over the internet to their cloud infrastructure. So that's like one aspect of it. Like I think the strategies are different. Also, I think it kind of depends on what data you're getting, right? If it's video streaming data on what is the live feed of the car, like then you start getting into some of those maybe considerations on if in an area there's thousands of Uber drivers and you like start getting video data, then you may start getting to some of those cellular connectivity issues. But we haven't really like kind of thought about that too much because right now it's very metric based and battery level and some of the more easier metric based systems.
That also leads me to my next question. So,
Okay.
you mentioned that currently OEMs like Tesla, GM, when the vehicle requests an API, the OEM's cloud infrastructure directly requests that data from the vehicle. So, why have they chosen that path instead of working with wireless providers? Because if you think about it, if for each vehicle that they have to maintain a open session for each of the vehicles.
Correct.
But if they work with wireless provider companies, they can leverage the existing wireless infrastructure that these wireless companies already have. And wouldn't that speed up the data transfer process?
No, I think that's a really valid question. Like, I don't know the choice there, but I also feel like the ecosystem is fairly new. So the providers are also starting to figure out like those impacts and how to actually structure this in a better way.
Okay.
Yeah.
Thank you.
Yeah.
There's a question from the audience.
Oh, yes.
So asking, you can read it, right? So for 95%, so who is paying?
What this is saying is that like anyone who's going and buying a new car, the car is connected.
Yeah.
So
Whether or not you use it is
correct.
who is paying this bandwidth, for example?
So it depends on the OEM. Like this, I think it's dependent. For example, if you buy a Tesla, the connectivity is included in the price, so you don't need to pay anything extra. But certain companies, for example, I think BMW has a package where they charge certain dollars a year to have like connected services included. So it's a very OEM specific choice on even if they're bundling that feature in, like the SIM card or the communication costs, like who bears it. Some are including within the MSRP, some are like charging as a service add-on.
Okay, so does that mean it's always cellular?
So now we talked about like connecting to external API, getting the data into Uber systems. How do we like now build a system to continuously get the data from these vehicles, right? So you have something called as workflows. So what we do is we have a highly scalable system called Cadence at Uber, which is an in-house built workflow system. So every time a vehicle goes online, we spawn a workflow. The workflow is very dedicated to that specific vehicle. And think of it as like a cron job running to continuously pull the data from the vehicle. What this does is it does separation of concern, saying that if the workflow fails, it's only failing for that single vehicle. No other vehicle is affected. Secondly, like you can terminate it because you know when each vehicle will go online and offline independently. So you don't need to like have this massive giant monolith that is looking after every single vehicle. Also, this becomes very extensible because now when to start a workflow can be tweaked based on different parameters. So for example, right now for our use case, we only care about getting the data when the driver is driving on the platform. But in other cases, as you can imagine, you may want to know, like, even if the driver hasn't driven for like 2 hours, what the current state is, do we need to nudge him to go and charge the vehicle because they're running low, right? So you could have other scenarios where you want to trigger these events for getting data collection. So this workflow system is more generic where it can support different type of triggers that go into data collection. Okay, so now we talked a little bit about the connected vehicles platform. I'm going to jump a little bit into batch-aware matching, which is the first feature we built on this platform that is live now. So the motivation for building this was, talked a little bit about this in the beginning, but we really want to filter out trips which are beyond a driver's range. So if you only have 50 miles remaining in your car and you send it on a 60-mile trip, that is going to be catastrophic. It's not going to be able to complete it. And poor experience for the driver, poor experience for the rider. So you really want to like not send them on a trip that you know they can't take. And the only way you can do that is if you know like what the battery level is of the car. Now, within that, like what also happens is like maybe the drivers are not taking these long trips, but even if they have 30% remaining on the car, they're like, yeah, I'm running low, I may run out, like Uber may send me on a long trip. They'll actually like stop using the Uber platform and go and charge. What you have now done, you have actually like reduced the utilization of the energy on the car. You still have 30% remaining, which is still a lot of battery left on the car, but the driver has like anxiety or range anxiety, so they will stop working. Yes, exactly. So, but if you have comforted the driver saying, we know your battery level, we are not going to like send you long trips, and we are going to make sure your trip ends close to a charger, then they can start depleting their battery more, and that increases the utilization of the battery itself. What that means for Uber is that like you get more and more like EVs operating and on the platform for longer, and you have more like green supply to tap into. So as you think about this, there are kind of 3 stages within this. So in a hypothetical example, let's think about stage 1 where a car has 100 kilometers of range. It has about 80 kilometers remaining, which is about 80%. So the remaining range is high, a lot of charge is still remaining. We are not filtering too much here. Like there may be still trips which are longer than 80 kilometers, but usually like if you look at the statistics, less than 10% of trips or like somewhere on that ballpark will be longer than that, and those get filtered out. So driver is not like still getting most of the trips. Some trips are getting filtered out. That's fine. They're operating happily on the platform. You really don't need to do any intervention, and they can continue operating as is. This is kind of the happy stage. The next stage is like now you're starting to deplete the battery, and but still sufficient batteries remaining, like between 20 to 70%. As you can imagine in this map, like now you start seeing like certain trips that the driver cannot take. Now it's at 30% remaining. There's like a 38 kilometer, 35, 110 kilometer. So slowly and slowly, more and more trips are getting filtered out. Still fine. They still have a lot of battery remaining, like, but based on not just the battery level, but other parameters, you can nudge them to charge. So for example, they're operating at 2 p.m., like the demand is low. So they don't need to charge right now. They can actually go and charge right now because demand is low. So even though they may have sufficient battery remaining, you want to like have them, you want to make them charge up so that they can be ready for like 5 p.m. High demand that happened in the area. So this is like more like extending battery wear matching in to figure out how to optimize for earning levels of the driver overall. But again, like the basic concept is that it's still operating healthily. You are limited intervention for the driver. Some less than half the trips are getting filtered out. Most utility comes in when your range is low. When you have less than 20% remaining, more than half, like 70-80% of your offers are getting filtered out. And then you are like now really recommending the driver, like you really need to go and charge, because at some point you're not going to get any offers, right? Because basically everything is getting filtered out. So to avoid that, then you nudge them to actually recommend them to go and charge. So those are kind of like the 3 stages when you think about battery wear matching. So let's quickly dive into the specs for this feature. So these are like some terms that we have defined. The way to think about an offer is kind of 2-part. The offer comprises of an en route distance. So when an offer is sent to the driver, they need to go to the location for the rider to pick them up. That's called like DCP, which is distance from the current location of the driver to the rider pickup location. Then there is DPD, which is on-trip distance, on how long the driver will take to go from where they are to where they need to go, the actual distance of the trip. So the offer distance is like a summation of those 2 values on how much they need to go to the pickup location and then from there to the drop-off.
So I think that just now you probably push the little button somewhere. So now this font is not very clear. You just something. Can you just unplug the
Okay.
again? No. Just now I noticed you put one button and all of a sudden now it became. Oh yeah, now it's better. What's that?
Is it better now?
Yeah, now it's much better.
Okay.
Yeah, just now it's right.
Yeah, there's some like
bigger difference because it all became like yeah, okay, now it's much better. What's that?
It's just this like brightness app for controlling brightness, and so probably that is doing something weird.
Now it's much better.
Maybe I need to quit that. I'm trying to figure out. Anyway, hopefully it doesn't happen again. Cool. So we talked about the offer distance. Then you have the minimum distance for an offer on how much is the minimum distance that we can send to the driver. And the maximum is like the maximum that we want to send them. So that's dmin and dmax. There's something called as a freshness threshold. We'll talk a little bit more about that on how do we think about freshness of the data and impact on the offer quality. Then you have remaining range. This is the actual data you're getting from the car on how much range is remaining on the car. We have something called as an estimation buffer that we apply on top of it. So not taking the remaining range at face value, because that can be inaccurate. It can be an overestimation or an underestimation. We try and be more conservative and then say like it's an overestimation and then apply like a correction to it. And the final thing is like drop off to charger. So you don't want to send them if they have like, let's say 30 miles remaining, you don't want to send them on a 30-mile trip because they'll have like 0 miles remaining at the end of it. So we add something called as a drop off to charger buffer saying if you end the trip, you should have still certain number of miles remaining. So you can actually go to a charger. That's called like DOTC, which is drop off to charger buffer. We talked about like the total distance is DO, which is DCP plus TPD. So the equation really becomes is like, if your data is fresh enough, then the bottom equation applies. But if your data is not fresh, then we kind of turn the feature off. So if you haven't received the reading from the car in like X number of minutes, half an hour, 1 hour, or whatever, like we know like we don't have any confidence to know how much is remaining. So you like kind of turn the car off. If the data is fresh, then what you do is you say that the offer distance can be between dmin and dmax. Dmin is kind of like MR, which is the minimum range cutoff, saying this is the minimum number of miles I want the car to have remaining, which in most cases will be like DTOC. Otherwise, what we do is we take the remaining range value, subtract the estimation buffer from it, and then also subtract how much you need to go to a charger. So that's kind of like the maximum distance you can take. And we like kind of have a graphical representation of it as well. Any questions on spec?
Yes, sorry. So the remaining range is captured from the vehicle, but the estimation error is learned through lots of data.
Correct.
Oh, got it. Thank you.
Correct. Okay, so let's talk about some of the factors that affect it. So why we need to have a freshness threshold? Now there can be multiple scenarios. So if the first one is like the car is turned off, then you expect like no drain to happen over time. If you're idling, then you may be stuck in traffic, you're not driving, but systems are still running. Maybe there's air conditioning, heating happening. So there is still drain occurring, but the slope is kind of low. You may be driving at a lower speed, and then the slope kind of increases. High-speed driving will further decline the slope. And then if you start going over altitude, where you're continuously accelerating, then that's where you'll have the most slope because the battery is like continuously engaged and degrading. As you can imagine that as time passes, the confidence on range kind of goes lower and lower if you haven't really fetched it. So if you haven't fetched the data, let's say in 15 minutes, it's potentially like you could have lost 30 miles or maybe more, depending on how much capacity the battery has. So that's why we like introduce this concept of data freshness to say that because of these wide variety of scenarios, we are going to have like a static threshold and saying after a certain amount of time, if we haven't gotten the data, then we are going to turn the feature off. That, of course, is configurable and there are other parameters that affect it, but that's kind of like the genesis behind that parameter. The second aspect is like charging time. The bottom 3 bars are kind of carryovers from last chart, but different vehicles have different charging rates. So for a Chevy Bolt, it likely is a more linear graph, depending on what kind of charging speed it's using. So if it's like an L3 charger, it's like more flat. Whereas like maybe if you're on a fast charger on a Tesla, then you have like a more parabolic curve. Now that has impacts on your drop off to charger distance. So if you're going to be able to charge much faster, you can have a lesser drop off to charger distance because you know like you can get there faster and then like your charging is going to increase faster as well. So to account for this is why we introduce the drop off to charger buffer. The final aspect here is like estimation accuracy. So again, like what we saw is that the remaining range we get from the vehicle itself is not super accurate. it varies widely. It can drop, it can increase again, even if the driver has moved, a vehicle has moved. So to account for that, like we use something called as a multiplicative buffer to say, right now it's like percentage. So if if it's percentage based, then as you have more and more like remaining range, you are like accounting for more and more buffers. So for example, if the vehicle has 300 miles, then you say that the buffer is 10%, then you're kind of subtracting 30 miles from the range. But if you only have 30 miles remaining, that buffer will only be like 3 mile estimation accuracy cut that you will take. So it's more like a diverging graph, as you can see here. And that's how you try and like guard against that. The estimates on the car may be like inaccurate. Okay, so if you put it all together, this is what comes like. So the black line is a scenario where these are the raw values that you're getting in from the car. The first thing is like you subtract a fixed distance. So let's say like we use 8 miles as the drop off to charger distance. So if you have a lot of miles remaining, like that 8 miles is really not going to affect it. But as you have like lesser and lesser remaining range, like that sort of slope decreases quite a bit. And on the y-axis, you have percentage eligible trips. So if you're like have remaining range and you take out like a fixed miles from it, then the number of trips that you're eligible for like decreases exponentially as your remaining range drops. Then the way to think about like the estimation accuracy. So if you were to take like 10% as estimation accuracy, which is this dotted red line, then it's almost like going in parallel to the red one. Obviously, like the difference is like much lower at the higher end versus like at the lower end. And similarly, you can play around with these parameters. So you can increase the drop-off to charger distance to 15 miles. And then like if you take your estimation accuracy at 25%, then this black line actually becomes this dotted blue line. And it's much lower, right? So now you're taking a lot of like cut and being more conservative. So as you can imagine in here, you can have an ML model to figure out the right parameters to choose based on OEM, based on the charging network, charging speed, algorithm accuracy that the OEM has put in place for their algorithm as well for remaining range. Okay, so this is one of the features we built. I think there was a question around this. So for all these 3 stages, like what is the optimal fetch frequency that we want to have? So we initially implemented with like a fixed value, which was fairly like consistent for like a few minutes. Every few minutes, regardless of how much range you're remaining, we'll kind of pull it. But as you can imagine, like if you have a lot of miles remaining, if you're in stage 1, you don't need to know the range every like 5 minutes, for example. You're okay like knowing it at a lesser frequency. And that's how you can manage some of the volume of the data as well. Because usually like you'll have most of the cars operating in BAM stage 1 and stage 2. So this is kind of like a before and after graph. So right here is when we deploy this feature in, and the calls actually decrease by like 3 to 5x. So that's like one of the levers we have is to now use something as more smarter on the polling side. Okay. Finally, like we have integration with matching. So matching is Uber's system to now generate offers based on a bunch of parameters saying, hey, here's a rider who needs to go from A to B. This is the closest driver, or like these are the bunch of drivers that can potentially take this trip. Who do I send it to? So that's the matching system. And then this algorithm actually is plugging into that. But the scale of the system is massive. So how do we optimize for that scale? So we implemented like 3 things. One was pre-filtering, saying not every vehicle is electric and not every electric vehicle is connected today. So we have a pre-filtering saying we're going to pre-filter the vehicles, and only the vehicles that are enrolled need to go through this matching like integration. So that drastically like cut it down by a magnitude on how many times that system was called to get this batch data. The second aspect is caching. As you can imagine, like the range is changing like every few minutes, but an offer may be being sent to the driver every few seconds. So they may choose to decline an offer and they may want to wait for another offer. So in that scenario, like your system can be called multiple times to know what is the battery range. Now, if the system is being called like every few seconds, like the range hasn't changed, we are polling at like minutes frequency. We don't need to, the data is not changing. So we built like an internal cache to now like cache this data with a TTL so that we can serve it directly from there. So this sort of shields the lead from, this is our online data store that has the raw data. And the final thing we talked about is like fail-safe. So matching is like very critical, right? Like this is one feature that's going into it. Maybe everything was fine, the data was coming from the system, but our service was down. So we obviously don't want to bring down like the whole matching algorithm. So we build like a fail-safe mechanism to say, if for whatever reason, maybe the data is not fresh or our service is down, we are going to like have an escape hatch and like not provide any data back, which means matching can function with BAM basically turned off. So those were like some of the considerations that went into building batch-saver matching.
Good question. So was there any thoughts on hosting an edge server on a vehicle or on the infrastructure to speed up the filters, the search?
No, not right now. Like one, we are not at that scale where we need that sort of layer at the edge. The second is, I think it also depends on who that edge layer will talk directly to. So because we are working with like a couple of data providers, like that component is not something that is in our current architecture.
Thank you.
Yeah. Okay, so let's quickly talk about consent and authorization. There was a question around it. How do we actually get the right driver consent? So we build this experience within the Carbon app or like driver app. So Uber drivers have multiple ways that one, they can discover this feature that they have brought on a connected vehicle to Uber and they are eligible for batch-saver matching. That's kind of the discovery phase. Then you go into like, yes, they want to consent and opt into this feature. That's the consent experience. Then they go through an authorization experience where they're logging in and then providing their credentials through like the third party to get the OAuth token generated so the data can be fetched. That's the login experience. And then finally you have like kind of data sharing, which is like a management page to say these are the vehicles which are connected and are sharing or not sharing data. I'm going to dive into like each of these really quickly. So on the discovery, we have like 3 different ways where the drivers can discover. So the 2 major surfaces are Carbon inbox and Carbon feed. Think of it as more like a feed notifications that drivers are continuously getting on opportunities. So one of the feeds says that like, say goodbye to range anxiety, you can opt into batch-saver matching. That's one way for them to discover. The second is like they're already driving and then while they're driving within their feed, they will get like a notification saying you can opt into this feature. And the final aspect is like in the management or like settings within the app, there is a tab for vehicles. So within that like page, you will have the share vehicle data button added onto there. So as you can imagine, like there are different ways where drivers can discover they are eligible for this feature and can opt in. Next up is consent. So regardless of where they get into, if they tap into any of these 3 funnels, they will be taken to a consent page. The consent page basically talks about what the data is going to be used for. Why is it like beneficial? And then within that, there is also like terms and conditions that they can view and also learn more about the feature. This is very simple. It's one click, you click on that, and then you get taken to the next page. What we call is we have 2 types of consents. One is a master consent saying you're okay, like sharing this data, which we are calling as like the master consent. And there is a vehicle level consent saying you need to enable connected vehicles on this specific vehicle. So once you've kind of provided the parent consent, you are taken to something called as like login experience. But before I jump into that, like in here, if you look at this page, there is a learn more. So we build like an FAQ that talks about all the different reasons why this feature could be beneficial to the driver. The login experience is quite simple. So after they click the toggle the connection button on within the page, they will be presented on some privacy settings, and then they will be taken to the login page of the provider. So right now we are enabling it for Tesla. So this is kind of like the Tesla web login. They need to punch in their email password. When they sign in, then they are shown what data is actually collected. So these are granular permissions. And as you can see that this is only battery level that they are kind of allowing access to. Finally, after they have like successfully connected, this is the management page where they can continuously go and see what the what vehicles are connected, and they can also disconnect if they want. There could be scenarios where automatically the vehicle gets disconnected. So for example, the auth token expired And then this page actually will show that that's off. So they can go and reconnect. So this serves as like the ongoing source of truth on how this is managed for the driver. Okay, so this is like the overall end-to-end user journey for consent and authorization. So they can discover the feature, tap in and provide their consent. From there, they are taken onto the authorization experience, punching their credentials, providing access to permissions, and then continuously be aware on what data is being collected and from what vehicles. Okay, I want to quickly play a video. So Uber had its event actually on Monday this week, where Sachin, who leads the driver app within Uber, presented this feature. So I want to like play that for you. Let's see if you have audio. No, maybe I can use my.
Hey, when should I charge? Let's say but the other questions that we get is, hey, when should I charge? Let's say if I'm at a low battery level, let's say you're at about 20%. Now, if you get a longer trip, should you take it? Should you not take it? How many miles can you squeeze out of this? So we're trying to help with that as well. And we do that by asking your permission to be able to share your car battery level with us. If you were to give us that permission and we have access to your car battery level, let's see then what we can do with that. Let's say you are at about 22% or so, and you're about to get a trip that looks like that. It's you all know how long that is. It's about an hour and 15 minutes. What should happen in that case? Even on that good day, we probably don't want to send you that trip because you do not have enough battery life, right? But that doesn't mean we don't send you any trip. There is this other trip, which is about 6 miles, which you should be able to complete with the battery level you have and still make it to the charger. We call this battery-aware matching. So we should only be sending you trips that you can actually complete.
That's a live demo of the feature. It's actually live in the Uber app, and yeah, a lot of drivers are already using it.
But the other
any questions before moving on? Yes.
So the question about ban at point. For EV vehicle owners, so Uber doesn't consider which charging station that they'll charge at. It just lists the closest charging station, right? Because for some car manufacturers, they have collaborations with, for example, Electrify America, where they get free charging. So some of the Uber owners that I know, they prefer to charge at specific charging stations. But
they don't need it. They know where it is.
Yeah. But the EV matching doesn't take that into consideration. Right?
So the extension to this feature will be that. Right now, we only use a battery level, but the next version is charger-aware matching, where you know where the chargers are. So you will like take them and end the trip closest to a charger. So that's kind of like the next level of optimization we want to bring onto this, to know like where the chargers are, what is compatible, what is available. We have real-time data on what the pricing is of a charger, where it's located, if it's fast charging, slow charging, and if it's compatible with the driver's car as well. And then using all of that, figure out the right time for them to send them to the charger.
And then for the having charger availability, how do you plan on solving that problem? Because for ChargePoint and Electrify America, in the app, they'll say it's available, but then when the driver is there, it's not.
So we have like partnerships with aggregation companies that give access to like charger availability real-time data. So that's how we are like today in the app. If you go and Uber has something called as an EV charging map, very similar to how you see gas station, you see EV charger. And if you tap on a charger, you can see like how many slots are remaining that you can charge on. So that data is available through like third-party API.
Okay, and then you're assuming that data is valid instead of.
Yes, I mean, so we, right.
I drive an EV, so on my trip to Virginia just a couple of days ago, Electrify America said these chargers were available, but then when I got there, they were at reduced power, or they weren't anything at all.
Yeah, so there can be like scenarios where the data is inaccurate. So I think over time you can apply, you can build like real-time feedback from the driver saying like, hey, you said it's available and it's not, and then pass it back on to the charge point providers as well to fix some of those accuracies. So I think that's a very valid concern, is that you'll, for now, like we take it at face value, but eventually you can try and like have some sort of feedback loop in there as well.
Oh, thank you.
Yeah. Okay, running a little bit over. So I'm gonna quickly talk about AV vehicle control. So this is the second feature we built on the connected vehicle platform. What we really wanted was AVs. Uber is now like partnering with AV companies to bring them onto Uber platform. So we wanted a way to like now state change and send commands to vehicles. As you can imagine, like there is no human in this car. So a lot of operations need to be executed remotely. So the requirements for us was, the first is before you even change the state of the car, knowing what the current state is. So is the door locked? Is it unlocked? Is the like window on, up, or window down? So the first step is to know the current state. The second is that like you need to remotely change the state in a secure way, because now these commands are going across, like these vehicles are not Uber vehicles, they are like Waymo and other companies. So now you're kind of going across company boundaries. So how do you do this in a very secure and reliable and in a private way? That was one of the requirements. And then eventually, like, how do you build that so that it's reliable? So you may like push the button and the driver and the rider may say unlock a vehicle, but the vehicle did not unlock, right? Like, how do you provide that experience so that when the rider is pressing unlock, reliably it gets executed? Which basically means that on the back end, you need to be aware on if this is successful. If it is not successful, then like resend it and then continuously do that in a way where it is successful, and then you can provide that back to the rider. So for these, we designed this state machine. When you look at the state machine, it starts where the rider has requested the car. The car is now like at the pickup location, and then at that point, like from the car, you will know the vehicle is parked. Now, if it is parked, that's when you can start even unlocking that functionality on the rider app for the rider to be able to press that unlock button. The first step is like this is a grayed out button, and then it becomes actually black, and then you can press it. Then the rider like presses on unlock. The next step is that you need to first verify whether this is the actual user who is authorized to perform this action. And then once you have done the verification, then you like send the request to the third party company. Now, like, because again, it's crossing a boundary, you need to verify the request is actually coming from Uber for the same rider. So there's like a dual verification that needs to happen to make this like very secure. Then after the request is verified by the AV partner, like they will execute the action on the vehicle itself. And then after it's successfully like executed, they'll send an acknowledgement back. If the acknowledgement does not come, like you can basically like create a loop around here where you like resend the request and then like wait for response. So you can imagine like how reliability is built in here. And then eventually, like once it's acknowledged, you can start showing the right state to the vehicle itself. Now, like when the door is in an unlocked state, then you wait for the rider to get in the car. They get in the car, the door unlocks, you know the state of the door closes eventually. And then like once that happens, you can automatically lock the car and start the trip. So that's how you now like a lot of this functionality is being built on the connected vehicle platform. Okay, time for a second demo. So let's see how it looks in person.
And then press the unlock button.
Pressing the unlock button, and there you go. The door opens. It's
right, open the door.
Okay. Yeah. I think they're customizing a Hyundai Ioniq vehicle.
No, the ironic.
Yeah.
They're also partner with a Pacific. With a van.
Maybe. I think so. I'm not sure. Yeah.
Oh yeah, the first.
So that's a very quick demo on how we built vehicle control or AV vehicle actions. And over time, we see a lot more value. So for example, Uber is getting into car sharing, similar to how Turo is. So as you start renting these cars, you don't need to have the owner of the car give you the key. The owner can directly unlock the vehicle and you can get in and start controlling the vehicle. Any questions before moving on?
that unlock option is all implemented on the network, in the network to make the work right.
Yes.
So you consider that sometimes when the user getting very close to the network, they want to then it's kind of the Bluetooth or the gas to unlock the protocol in case that the network is not working.
That's a really good question. Like right now, everything is happening over internet connectivity. So if the writer like does not have cellular connectivity, like there's no way for the writer to communicate with the app itself. So that is a challenge. I don't know how to solve it for now, but yeah, like the assumption is that you will have connectivity to send this command through the Uber app. Correct. Yeah, you can have like obviously fail-safes built in where you can tap something on the vehicle and like do it. But I think to your point, to do verification is hard. You can build mechanisms where you have a PIN. So like on the Uber app, maybe when they requested the ride, they knew like this was their PIN, and then they can punch that PIN into the console of the vehicle itself. So you can have maybe like some sort of an offline verification that can happen in that scenario. Yes.
The question is, we also use Bluetooth
No, not right now.
to parallel the secure for security. Like, I think in China, we used to have a, if you want to drive a shared car, you do car sharing. If you want to drive a car, shared car, you need to connect to the connect to the internet and connect to the Bluetooth. So they have two security methods.
Interesting. Yeah, I can.
Scan your face to do identification.
Yeah, right now, like this is again in a pilot phase that's happening. So over time, I think more and more such features will be added on onto the platform for sure. Yeah, that's really interesting.
In China, they are very good at for all kinds of fraud, because there are many frauds. That's what they pay a lot of attention. I noticed that 5 years ago, every bank is using two-way authentication. At that time, pretty much no. I think it's recently started. They're sending a text message on this.
Two-factor, yeah.
Yeah, but we tried to deploy this quite a long time ago. Deal with this potential.
Yeah, I think like AVs are definitely in a more advanced stage there for sure. And I know like DD is doing quite a bit of work for sure. Okay, so jumping on to green vehicle identification, do we have a hard stop at 3?
No, because after this, we're gonna go to our lab.
Oh, okay.
This guy gonna show you.
Okay.
So he's,
Sounds good. So I can, it probably take another 15 minutes. So let's talk a little bit about like why we needed to build something called as green vehicle identification. Identifying green vehicles is very important for Uber for a number of different reasons. One is obviously we need to know which vehicles are green so we can send them on green, comfort electric, some of these like more sustainable trip options. Second is that for Uber to become a zero emissions company, we need to know how much emissions are happening right now on the platform. And if you don't know like the engine type of these vehicles, then estimating carbon emissions is extremely challenging. The third is that there are a lot of internal KPIs on how many EVs are there, how many hybrids, plug-in hybrids, fuel cell vehicles, and using all of the data, computing metrics like grams per emitted, per passenger mile, and things like that. So it's very important for us to have very detailed categorization of green vehicles and not just like EVs versus not. And then obviously, as you think about building experiences, like we talked about battery-aware matching, then you need to know like, hey, this is an EV, this is a connected vehicle, and now I can make it eligible for battery-aware matching. So for some of these sustainability experiences, then knowing the engine type of the vehicle is very important. And through all of that is how we will make Uber like zero emissions, which is the public commitment by 2040. Okay, so this is a quick graph. It's not super up to date, but right now, like in Europe, about 6% of 7% of trips are electric. And then in US, about 4% are happening on fully electric vehicles. So that share is like definitely growing over time. And as more and more green vehicles come online onto our platform, knowing the engine time becomes even more important. So why is it hard to know if a vehicle is hybrid, electric, or fuel? or gas vehicle. You can imagine like something like a Corolla comes in gas variant, it comes in a hybrid variant, and maybe in future will come in an EV variant as well. But it's named Toyota Corolla. So just knowing like the make and model is not enough. Also, if you have information like the VIN number of the vehicle, then you can plug that in and figure out what the engine type is. But Uber does not collect VIN information in all markets. VIN is not available in all countries globally on the documents. So in a lot of cases, we don't know the VIN number. So because of these combinations, it's very hard to know with 100% accuracy what the engine type is of a vehicle. What that really means is that if you don't know that, then Uber has incentives. So if you bring an EV onto Uber platform and do a trip, you get $1 extra. So if you have incorrectly identified or not identified it as an electric, then drivers are actually losing out on money. And with drivers doing like hundreds of these trips, like there's a lot of material money that we are not paying to the driver. Also, if you have incorrectly identified a gas vehicle as electric, and then you call a Uber Green and a gas vehicle shows up, it's a very poor experience for the rider. Like that's not what they expected to see. And then obviously, like if you don't have very clear identification, then you will not be able to do like very correct reporting. So Uber is leading the industry on having transparency on emissions that the platform is generating overall. I'll talk about like the examples. So today, like what happens is drivers bring an EV onto the platform, and then somehow before the system came into place, it was not identified correctly. So they'll go into an actual like green light hub location, which are like Uber centers, and say, hey, I have an EV, it's not working. And then they'll be like, yeah, show me a photo if it has a tailpipe. If it has a tailpipe, it means that, yeah, it's not an electric vehicle and not. So it's more like a visual verification that's happening or was happening, which is obviously like a poor experience. They're wasting time like going into a hub and getting it verified. So how do we like kind of solve this problem? So the first step starts with knowing where we can get this information from. So there are kind of like 4 different ways that we have so far. One is VINs. We just talked about this. It's a globally unique identifier that can give a lot of information. Then you have documents. A lot of the registration and insurance documents do list out what the engine type of the vehicle is. You can plug into that. Then you can have like make model rules. So for example, we know like it's a Tesla, it's going to be electric. So there is no ambiguity in that scenario. And then obviously you can also hook into some of the manual processes that we just talked about, where you can have drivers sending photos of the vehicles or they're actually taking it into a hub. So we do support like taking some of those manual inputs into our system and automating around it. So the first and biggest one is like VIN decoders. VIN, again, like a 7-digit unique code that is assigned to each vehicle. Probably everyone here is very familiar with this one. But what we do is we take that VIN and connect it to a third-party decoders, which will give us like lookup on all the different spec of the vehicle itself. And through that, now you have very high level of confidence on what the engine type of the vehicle is. The next one, I talked about registration and insurance documents as well as photo verification. So these are again documents, and within those documents, we have auto transcription to read like each field, and through those fields, we can figure out whether it's an electric or not. Obviously, not all regions have it, but in France, for example, it's mandatory to list out the engine type on the document itself. So we like encode that and plug it into our system. The third piece we built is a make model year classifier. And the data model behind this is based on a make model and a given region. You can manually say that, for example, a Toyota Corolla in France after 2019 is all hybrid. So you can define that rule, and then now any vehicle that's onboarded within that region automatically is classified using that rule. So it becomes a way to now en masse define these rules, so you can now start classifying models fairly accurately. As you can imagine, like there's some sort of prioritization here. If you have the VIN, you also have the document, and you have a make model classification, which one do you use, right? So we define, the way system was defined was to have some sort of priority. The priority is given to like documents first, then it goes to VIN, and then like finally it falls back onto make model classifier. So if you have multiple sources, like we use some sort of prioritization based on our confidence level for each type. Okay, so why did we define all these different types, right? So one is if you have VIN and documents, they're very high accuracy, but they may not be available everywhere. Also, like because you have to connect to third-party APIs, the cost can be higher. You can trade that off by a little bit lower accuracy and lower cost by plugging in make model classifier, as well as like leaning on manual processes. So the design principles for this was to make it as accurate as possible, reduce errors. It should be quick. So previously when we were doing this, it was taking multiple days for it to happen because it was an offline process. Now like that shortened down to like kind of minutes and hours. Also, we need to have one standardized way. We talked about multiple uses of this data set. So having a single source of truth for this is important. Accessible, have multiple people within the company able to use it. And then obviously we want to make it as affordable to do this for the company itself. So this is a quick overview on the architecture. I'll break this down into components in further slides. The one thing to call out here is the black boxes on the top left are the documents that we are plugging into. As these documents get transcribed, like they create events that go into like the event processing system. These are all the third-party vendors that we are connecting to do like bin lookups. So for each different region, you have a different provider for doing lookups, and then we are hooking into each of those providers to get that transcription done. Okay, so let's quickly do the event triggering and part. So as these documents get transcribed, through those we will get mutation events. So for example, now when the vehicle registration document is transcribed, we know the VIN number is decoded. So now the VIN number flows into our system, and then automatically, as soon as that happens, we now take that and then plug it into a VIN decoder. So instantaneously, when that transcription happens, then the lookup of VIN will happen, and then we'll like save that information into our like VIN store, and then save the fuel and engine type of that vehicle itself. Interestingly, like one of the things can happen is you can have multiple such events happen. So for example, as the document was getting transcribed, you got the VIN, you also got the engine type from the vehicle, you also got the make model year, because all of that information is on the vehicle document. So which one do you process first? Like if you process out of order, then your rule priority engine like is not being applied accurately. So we do something called as an aggregation. So we like kind of batch events for a given vehicle for certain minutes, because and then basically dedupe. So if you know, like for a vehicle, if you have multiple processes or events that come, we only like dedupe and execute on that vehicle once. So that allows us to implement this priority engine in a more clean way. And then finally, like all of these will go through a Kafka consumer, which is essentially like a processor, and the processor is applying either looking up through the VIN decoder, or it is looking up through like the make model year rules. So that's where like this computation is running. The next thing is like something called as a VIN store. So we want to have a centralized store to know for a given VIN what the information is associated with it. So that's where like this VIN store is stored. So for example, you can have scenarios where the same vehicle is getting onboarded multiple times. So I'm bringing the same vehicle to Uber. My like partner is onboarding the same vehicle. I don't need to look up the VIN number twice. It's the same information. So we are caching that within here. Also, this is an online store. So we want to run like a scheduled workflow to say, we also want it in our offline data stores. So we like run, again, Cadence is our workflow system for taking that information from an online store onto like an online store. The final step is like now we know the engine and fuel type of this vehicle. Then we want to plug it and make it eligible for Uber Green, Comfort Electric, and give it incentives. So the right half of this slide is the system called Flow that we use within Uber, which is essentially like an event-based automation system. So it'll take those events. So when we know the engine type, we actually now fire an event ourselves that the system is consuming to make the vehicle eligible for those incentives. Why didn't we like encode this logic within the workflow itself? So the good part about this is, one, it's UI. So there are different logics. So for example, when you think about Uber Green, the definition is not standard. So in certain markets, like only EVs are eligible for Uber Green, but in certain markets, EVs and hybrids are eligible. So you need to have those regional nuances to say that in certain markets, this combination of vehicles will be eligible for this product type. So this system allows operations teams to come in and define that logic based on the triggers that are happening. So that's why we wanted to provide that flexibility to our operations team, and that's why we plugged and kind of build this automated workflow that can be now hooked onto it. Okay, so finally, like what's the impact that this has had? So one is faster processing. It was taking up to 3 days previously before the system came online. Now we have like a P90 SLA of 5 minutes and P99.5 SLA of an hour. So essentially, like every vehicle within 1 hour of it getting onboarded to Uber will become eligible for these product types. Also, the good part is increased reliability. Previously, what was happening is because this was a batch process that was happening like once every couple of days, if there was some sort of failure, then any vehicle that got onboarded in the last 2 days would actually like fail. Because it was a batch workflow and one failure could like kind of kill the whole thing. But now we do isolation for every single vehicle. So failure on one single vehicle does not impact other vehicles. So there is a lot more reliability within the process. We talked about toll, there was manual processes running. So now like they have been eliminated. So we are saving like multiple hours every week. And finally, we have like one single source of truth that can be used by all different like product teams within Uber and analytics team to use for different product use cases. That's it. Any questions?
Okay. Questions?
Yes.
One more question. So,
Mhm.
As more and more connected vehicles come onto the market, that would make the GDID much simpler, right? If you could read its
Correct.
well, if you can read its battery,
Mhm.
then it must be in hybrid or EV. Yeah.
Correct. Yeah, exactly. And you can know like even if it's gas vehicle, right? If it's connected and you're onboarding it, then you will know the engine type. That's true.
Thank you.
Yep.
Do you guys, I'm thinking for anybody who registered to be a Uber driver, you do a little bit of background checking.
Correct.
And vehicle stuff. Right? At that time, can you collect any information?
So we get their registration document, a vehicle registration and insurance. So in there, if the engine type is listed, then we are able to know. But if it's not, then it becomes really hard.
Okay. Another question is, I just experienced in Boston last weekend. So I was calling a car. The car is very safe, it's driving. But then, in the middle of that, they switch it to another driver. Come, eventually the guy come here, pick me up. It's not
Yeah.
the original. Because, but this is not from
Yeah.
This will come from Lyft. I was like, how can this happen? So putting in this context is it possible, for example, William will be do the registration, we claim to the EV. But then when he really drive to there, he's using a different EV. In this case, we have no way. Do you guys have any way to know?
We don't. If it's connected, then probably, right? Like then you know the real-time GPS location of the car, and then through that you can do verification on the rider is here and he's requesting the car and the location, and you have real-time location from the car itself. So it's hard. That's a really hard problem to solve. The way that you know is that if you requested a car, you'll know like the license plate that's going to pick you up, and a different one comes to pick you up. So you start getting these bug reports from users saying the wrong vehicle is picking me up. And then that basically means that the driver is driving the wrong vehicle, and we have a notification pop up in the app saying, are you driving the right vehicle? So maybe what happens is if I, as a driver, have onboarded multiple vehicles, I may have just selected the wrong one when I went online.
Yeah, but you're not getting the same driver. The experience I have, even different driver.
Hmm.
It's completely, it's just someone else showing up.
Yeah,
Good news is, he said, he gave the explanation, but the previous driver don't want to go to Boston Airport, because after getting there, return traffic in a lot of traffic.
right.
So, but he loves the traffic, so he just drive me. Well, he didn't charge me anything as special, it was $10. But I was like, how can this thing happen? It shows for some of the Indians drive a wide car, and then it's somebody else coming in with a totally different driver, different vehicle.
Hmm. Yeah, those are like definitely hard problems. You have like some mechanisms, but you can't fully eliminate it. I think that.
But this event, if the guy, the same guy, is hijacking something.
Yeah. I think connected vehicles can play a big role. If you can get real-time data, then you know, like at least the right vehicle is coming to pick you up for sure.
Like, are we using this connected vehicle verification?
Mhm.
Sort of.
Yeah.
Mm-hmm.
Yes.
Working on security, that's what I
Nice.
care about.
I think that the network potential but it is problem.
Can help, not necessarily solve.
Yeah, but like in the future, if the you know, like refuse the job or we don't want not willing to connect with the other.
Yeah, and we see that, right? Like we opened this up to a lot of drivers and not everyone opted in. So there is definitely like trust building and value proposition on why the driver should provide this data. So I think over time, the way that Uber is approaching this is if there is very high value for the driver, then they will opt in, right? So as more and more features come online on connected vehicle platform, then it becomes more advantageous for them to share this data. If they know like providing this data will increase their earnings, like why would you not do it, right? So some drivers may still opt in. They're like, no, I don't want to provide this my data. But that's kind of like what we want to do is we want to build an ecosystem which is driving real lot of value for the driver itself. Yeah, but that's like a really valid point. And also it may happen that I bought a Tesla or like whatever EV, I never set up my account. If I don't have my account, I don't have my credentials. So I want to share the data, but I never like kind of signed up for the account on the OEM platform. So there are like other aspects of it other than just sort of the privacy and consent portion. Are we done? If you're done, we can stop recording.
Yeah, can we stop the recording? Let's thanks our speaker. You're like, this is really interactive, right? You can
Yes.
ask a lot
No,
of questions.
I really enjoyed on this asking questions.
Sure,
I just
sure.
want to get a photo with everybody, like if that's
Sure,
okay.
sure. Well,
Yeah.
can we get a photo? We can ask somebody.